Okay, Bismillah ar-Rahman ar-Rahim, Alhamdulillah, salatu wassalam ala Rasulillah. We will do the last part or the last few questions in worksheet number 2. In fact, we'll do question number 8, number 7, number 8, and number 10. So these are the only 3 questions that we did not in class, but the other questions we have done them in class, and they are very straightforward. Okay, so let's start with question number 7. Question number 7, in fact, it's somewhat easy. All it says that you have 2 spheres, and each one of them has a radius r, and they both have the same. Oh, no, actually, no, they have different type of charges, and he wants you to find the electric field at a point P that is located on the middle, or at the middle of the radius of the sphere number 1. Okay, so let me just sketch that over here. So get this out of the way, and if I sketch this, you have 2 spheres. Sphere number 1, sphere actually number 2, sphere number 2, and then they're just attached to it a sphere number 1, and each one of them has a radius r, okay, and one of them has charge q2, and one of them has charge q1. And what does he want? He wants to know if the electric field is 0 at point P. Point P is right here, right in the middle of this. So this point P is located half r, or r over 2 from within sphere number 1, and it's located within r and r plus half, so 3r over 2, so 1.5. So this is located r 3r over 2, which is 1.5 from here. Now, so if we, and again it has charge q, and he told us that the electric field at this point is equal to 0. Now, how do I solve this question? That's of course that's the question that we wanted to now elaborate on. Okay, so what I should notice is that all he wants me to do, he wants me to calculate the electric field. If I just take each one of them, he wants me to calculate the electric field for this. He wants me to calculate the electric field at point P, which is outside the sphere, and at a distance, as I said, this distance here is equal to 3r over 2. That's what he wants me to do. And also he wants me to calculate the electric field of, this is for point 2, for at some point here inside. So he wants me to calculate, this is the same point P. I just separated these guys so that we see it. So this he wants you to calculate inside the sphere, and both of these guys are insulating spheres, so the charge is uniformly distributed throughout the sphere. So the question becomes, I want to calculate the electric field here and the electric field here. Remember, the electric field at this point will be this way, due to, so let's call it E2, and for this guy at this point here it will be this way. This is E1. So in fact it will be E1 minus E2. That's what the electric field be, and of course that will be equal to 0, and then I can work from there. Okay, let's do this very quickly. So so if you remember, for a sphere, an insulating sphere, E inside is equal to it was equal to q over 4 pi epsilon, and then we have r over r square cubed. Okay, and E outside, we have calculated E outside to be q over 4 pi epsilon, and then we have 1 over r r squared. Small r is the small r will be the Gaussian surface radius. Okay, so what do we have to do at point P? at point P, the electric field due to due to charge 1 will use this one, and the electric field due to charge 2 will use this one, or sphere 2. So this will be sphere 1 and this will be sphere 2. And of course the only thing that I have to worry about is that what is the value of small r for both of them. Okay, let me just leave this in front of me. All I have to do is just calculate or plug in what the value of R is. So let me just say E1, which is the electric field due to charge 1 at point P, is equal to Q over 4 pi epsilon, Q1 over 4 pi epsilon. Now in these previous formula, I have also to do Q1, Q2. Okay? And then I have R divided by R cubed. Now R in here is equal to R over 2. So this is equal to Q over 4 pi epsilon R over 2 over R cubed. Okay? Which is simply Q over 4 pi epsilon. This comes in here, and then you get 1 over 2 R square. The R will go with this guy, and the 2 comes down. So this is E due to charge 1, and remember, due to sphere number 1 at point P, and this, the direction of it is outwards this way. Okay. The second one, the second one is E2, okay, E due to charge 2 or due to sphere 2 is equal to Q over 4 pi epsilon, Q2, 1 over 3 over 2 R all square. So this will be equal to 4, because this is, if you square it, 4, right? And it goes up. So that means it's 4 Q2 divided by 4 pi epsilon naught, and then you have 1 over 9 R square. This is 3 square R square. Okay? So this is E1, E2. If I add these, remember this guy is this way. Okay, E2 is directed this way and E1 is directed that way. If I add these two guys, he told me they're equal to 0. They add up to 0. If they add up to 0, then that means the following. E1 minus E2 is equal to 0. E1, which we said is equal to Q1 over 4 pi epsilon. And then I have 1 over 2 R squared. Minus E2, which is equal to 4 Q2 divided by 4 pi epsilon, and then I have 1 over 9 R square is equal to 0. If I take this to the other side, then I get Q1 over 4 pi epsilon 0. I have 1 over 2 R squared is equal to Q2 over 4 pi epsilon, and then I have 4 over 9 R square. Okay, so as you can see, this guy without the Q1, and this guy go. So what do I have? I have basically I have Q1 over 2 on this side. This guy stays and this guy stays, and then here I have Q2, and then I have 4 over 9. Okay, and he wants the ratio Q1 over Q2, or Q2 over Q1. Okay, so he wants the ratio Q2 over Q1. That means Q2 over Q1 is equal to 9 over 8, and that's it. Okay, so if you look here, if I want, I just cross multiply. Q1 becomes here, right, and then 9, 8. Okay, that's what I got from. That's what the solution looks like. Okay. So that's the solution to question number 7. Question number 8, again, it's very simple, but we need to be a little bit careful. Here, what is he saying? He's saying that a solid insulating sphere. So the first one is an insulating sphere of radius A, and then it has a uniform charge distribution rho and a total charge Q, concentric with a sphere uncharged. So the second sphere is uncharged, conducting hollow sphere whose inner radius is B and outer radius is C. And he wants to find the electric field at all the regions that's shown. Okay, and then plot the field and then determine the charge per unit to this. So I'll just do one A and B, and then the rest is very easy to do. Okay, let me show you what you have, what we have, and what you have to do, and all of these things that. Okay. So what I have, what he told us is he has this charge here, or this sphere, that is an insulating sphere. It has a radius A, okay, and it has some rho. Just some rho, and has a charge Q, and then it's concentric with another sphere that is conducting. So this is conducting sphere here, conducting shell, okay, shell, right, and it does not have any charge on it, okay, uncharged. There is no charge on this one, and the radii, this is B, and this is C. He wants you to find the electric field at all points. He wants you to find the electric field here, at this region here. Let's call it E1. He wants you to calculate the electric field E2, E3, and then E4. That's what he wants you to calculate the electric field in, at all the shown regions. Okay, remember this is an insulator. This is the conducting sphere. Okay, let's leave that in front of me. I'm going to leave that in front of me, and then I'm going to start. And first of all, for R less than A, okay, I can use the Gaussian law to calculate the electric field inside the sphere, and we've done that in class, and that's equal to Q over 4 pi epsilon, and then I have R over, in this case, A cubed. Okay, R is the radius, and R goes from R is less than A. Okay, R is less than A. So this is E1. Okay, that's in this region here, E1 inside the sphere. E2, which is R between A and B. So that means I am in region here. The only charge enclosed is this guy here. That means I am outside the sphere. So E will be equal to E2 will be equal to Q over 4 pi epsilon. Right? And the charge, now I have 1 over R. Okay, actually I should say R cubed here, or 1 over R square, and A is less than R is less than B. Okay, that's in that region over there. Okay, in region number, in the following region in here, the electric field E3 will be equal to 0. So E3 will be equal to 0 because I am inside a conductor, and we know the electric field inside the conductor is equal to 0 because the total charge, or the charge inside a conductor, is equal to 0. So this is where this is B less than R less than C. Anything greater than C, so this is E4. So E4 is somewhere here outside, way outside E4, this guy. Now I don't have any charge here, and the only charge I have enclosed is this guy over there. So E4 will be equal to Q over 4 pi epsilon, and then I have 1 over R square, and R is greater than, C. Okay, R is greater than C. If I wanted to plot these, it's very easy. So if I wanted to plot this, I just have to make sure that, okay, this is my E, and this is my R, and then, okay, I have A, B, C, and greater than C. So from A to, let me just take them one at a time. If I, from R less than A, I have a linear. So I have linear like this, and the maximum point here is equal to Q over 4 pi epsilon, and then I have 1 over A square, and then it will decay as over 1 R square, okay, up to this point here. So this is 1 over R square, and then it will be 0 in this region, okay, and then it will be 1 over something like this. It will decay something like this. The remainder, this also 1 over r square, and that's what the electric field looks like. Okay. The second part is just basically the charge. So this is part A. B. Determine the induced charge per unit. So you have to make sure that when you come in here, it's a 0 here. So that means the induced charge on this side must be minus Q. So if this is Q, this might be minus Q, so that gives equal to 0. And again, when you go outside, if this is 0, then you have to also calculate that as we did in the class. Last question. I'm just going to give you 1 or 2 hints on the last question, how to solve it, and the key to the solution. Last question, we have use Gaussian law to calculate the electric field due to uniform straight wire that is very long, infinite, and it has a charge per unit volume, per unit length lambda, and this time it's negative. What we did in class was positive charge distribution. This is a negative charge distribution. So this is my wire, and then I have negative this way. That means I wanted to calculate E. So using Gauss's law, EDA is equal to Q enclosed over epsilon, and the Gaussian surface I have is a cylinder. Okay, so that's my cylinder, and again I have to divide it into 3 parts. This is S1, this is S2, and this guy is S3. Now remember, the electric field is this way as shown because this is negative. So your electric field will be this way, and it will be this way. So that's your electric field. N hat in this side, N hat will be this way, and N hat will be this way. Okay, and N hat of course will be this way, and N hat will be this way. So this is N1 hat, N2 hat, this is N3 hat, N3 hat. So as you can see, these guys still, the angle is 90. So both S1 and S2 will give me 0 contribution to the electric field, and the only contribution is from surface 3. So when I break this to surface 1, as we did in class, surface 2 plus surface 3, so surface 1 and surface 2 will give me 0 contribution because the angle theta is 90 and cosine 90 is equal to 0. Okay, the only contribution I have is from S3. Let me very quickly do that. Okay, so the only contribution I have is from S3, and if I do that, okay, again, I'm running out of. Okay, let me go back to this guy. Okay, so I have E3 dotted with DA3 is equal to Q enclosed is minus lambda L divided by epsilon, because this here, this side, or the Gaussian surface that I constructed is L. By the way, this is the Gaussian surface. Okay, the Gaussian surface I constructed is a form of a cylinder that has 2 faces of area A, the same area, and a side of a length L. Okay, and the angle between, again I should go back to here, the angle between the electric field, which is this way, and N hat, which is this way, the angle between them is 180, so cosine 180 is minus 1, so I have E3 dA minus cosine 180 is minus 1, is minus lambda L epsilon naught, and of course the L will go, the negatives will go, and then I have E3 A is equal to minus lambda L over epsilon, and A, we know that it's nothing more than 2 pi r multiplied by the length L. Okay, so if I put these together, I get the following: E3 is equal to lambda, the L's will cancel, so this L will cancel with this L, and that's the area A over 2 pi epsilon. Okay, and then I have 1 over r, and this time it's minus r hat. Okay, because it is, if you look at where is my first, okay, this guy here, the electric field is in, so r hat is out, and minus r hat is in. Okay. Okay, that's what this indicates, and this is your electric field, and that's it. That's a solution. That's the solution for question number 10, and the other questions we discussed in class very well. So that's it for this worksheet, and I wish you the best. I'll meet you inshallah next time.